Right. Good morning, everyone. See. All right. Hope you had a good week. The sun actually decided to come out today where I am. The wind stopped blowing so hard and it stopped snowing yesterday. So sorry that we are not meeting in person today, but the weather just precluded me from driving across the Midwest. So hopefully, well, barring any 18 feet of snow or anything in between now and next Friday, I'll be able to drive back and we will meet in person and start working with the boards next week. We'll check out the boards, and in our next lab, I added in the hardware, connecting things to hardware. So we will be there in person. Sorry, I'm looking off, trying to see what my dog is up to. All right. So what I did today was I posted, so as you should be able to see up here on the screen in Canvas while you were taking the quiz, I just went ahead and added the pre-lab solutions, right? Just as a check for you to make sure your minimizations are correct for this lab, since it's a little more difficult for me to walk around and help people individually with their minimizations. So yeah, if you go to the pre-lab 2 assignment now, you can download this pre-lab solution PDF if you want to use that to double check your minimizations. And let me see, let me open that up here. All right, as a reminder, right, I hate when this opens this up in the browser. I'm going to open it up. With I'm going to open it. Here's my open with. There we go. All right. So I don't know, let's see, how many of you are in 1510 right now and how many of you finished 1510. So if you're in 1510, I'm guessing you should be hitting Boolean algebra in week 3. Sometimes the instructor will change the order of things, but you're probably newer to this. And if you've already had 1510, you're probably used to solving things with K-maps. And we will start using K-maps going forward in the next lab. But being able to use K-maps requires some understanding of Boolean algebra. It was never my favorite thing while I was a student. As soon as we got the K-maps, I was very happy. But then there will come a time when we work with XOR gates and XNOR gates when a K-map won't be able to minimize your circuit. So there are times we want to use the Boolean algebra. And actually, like I said, effectively using the K-maps is based on having an understanding of the Boolean algebra. Right, so as a reminder, right, this list here that I gave you then is basically telling you where the 1s and 0s are. The summation notation tells you where the 1s are and which rows of your truth table, right? That's a base 10 number. Decimal 2, right? And we have 4 inputs. So that would be 0010, right? When we convert it to binary. So all of these tell you where the 1s go in your truth table with the sigma or the summation notation. The product notation then, if you're given that, tells you what rows your 0s are in, what outputs are 0s, right? So typically you're not given both, you're given one or the other, because if we know where the 0s are, well, by default, we know where the 1s are, vice versa. If we know where the 1s are, then we know where the 0s are. Right, so hopefully, right, filling in the truth table was easier this week than working backwards from that complicated circuit equation of last week, right? And I just did that, right, to give you some practice there with the truth table and your binary numbers again. And then we want to write the canonical sum of products. And so basically, even when we move on to the K-mapping technique, what you'll do in the K-mapping technique, right, is you will map all these 1s and 0s over to a grid that makes it easier to pattern match and minimize your equation. But when you map all those 1s and 0s, right, and you write your equation, then you always have to include every single one and zero on that map. And so here, the canonical form.
Professor,
Yes.
I have a question.
Mm-hmm.
On the last line, the 15th line, number 15, 1, 1, 1, 1. The
Mm-hmm.
product, the product should be zeros, right?
Oh,
The
yeah.
sum are one.
Oh, shoot. Yes. Darn it. That probably just makes my whole solution wrong. Oh.
Oh, it's just the last.
Yeah, but it probably makes my minimization wrong. Maybe, maybe not. No, maybe it just makes the truth table wrong, hopefully. Here, let me fix this. My minimization hopefully is still correct. Thank you for pointing that out. I'm gonna save it and re-upload it. All right. And before I re-upload, let's just make sure there's no other errors in this. All right, so yes, this should be 0. All right, so hopefully that, right, my minimization, hopefully I did correctly. So canonical sum of products, right? That means you don't minimize the equation. The sum of products form then has all of the outputs that are ones, right? And we use the min terms for that, as we learned in the last lab, right? So this should be, when you start with a proof and you want to minimize, so when you want to minimize to sum of products form, you start with a canonical sum of products form and then see what you can basically minimize or remove from that using Boolean algebra. So this first term should be min term 2, which that should be 0, 0, 1, 0. This next term should be min term 3, 0, 0, 1, 1. I'm just checking, make sure I didn't make a mistake there. This term should be min term 7. So A is a 0 and then 1, 1, 1. This should be 1, 0, 0, 1. There's your 9. And then 1, 1, 0, 0. There's 12. And then 1, 1, 0, 1. There's 13. Right. And so once you start with that canonical sum of products here in your minimization, right? And I tried to give you some help here by showing you what the final form should be. A lot of times as a student, you're not told what the final form should be. You just have to find it, right? It's a little more difficult, I think, to do that using Boolean algebra than if you use a K-map. It's easier with a K-map to come down to the final form. With Boolean algebra, and when you work with K-maps, you'll find out with some of these minimization equations, there is more than one minimization equation that is correct that will produce a minimum number of literals. I don't think with this function, I think I can't remember. I'd have to map it out. I think there might be more than one solution, but I have to map it out to look at it. All right, this is what we're trying to minimize down to. And what we want to do with sum of products is we always want to try to isolate terms that are the term, like the term A, and we want to be able to OR that with A complement. So the Boolean law that says X ORed with X complement is equal to 1. That's what we're looking for, is that if we can factor things out and end up with a form of an input ORed with its complement so that it becomes 1, and then we can use the law that X ended with 1 is simply gives us 1, then we can remove terms, and that's for the sum of products form. Let's see. Okay. So David, let's see, 1054. We have 7 ones, but we have 6 min terms. That's what we were just talking about here, in the fact that here, right, there are 7. I made a mistake here of putting a 1, and there should be a 0 there, David. That's what we were just talking about before. I will fix that and re-upload it. I think that's where your question comes from. If not, let me know.
Yeah, I just wanted to make sure that I wasn't doing the wrong thing here.
You know, 1, 2, 3, 4, 5, 6.
And
What
one
did
in
I-
there.
Oh, I left out 8. Dang it. 1, 2, 3, 4, 5, 6. No, I left out 8. Okay, well, I guess I'm not helping you at all by giving you the supposed solution. Ah, this is what happens when I type it and don't write it out on paper. Get my Word doc. All right, so yeah, I ended up missing 8, didn't I? 2, 3, 7, 8, which is A, B naught, C naught, D naught. I don't know. So did I come up with the correct minimized form? I'm going to do a correct check here. Were you all able to show that that was correct? Did I just leave out a term in my typing, or do I have an incorrect solution? All right, Matthew
This
says
is good.
he was. All right. But pretty sure I K-mapped it to double check. But... All right. And so I'm just doing something quickly on paper. So I'm going to K-map this to 2, 3, 7, 8, 9, 13. Yeah, that I should end up with and AC non. Okay, AC not. And I gotta put 8 in here. 8, there's 8. But I now have to retype this. All right, let's go with this is your correct minimization for AC naught. And that's A naught. B, all right. A naught, B naught, C is correct. And A naught, CD is correct. So this is the correct minimization. I just left out a term here. I'm going to have to go back and insert that term and retype that. And I won't do that on your time. I'm just going to go back and reorganize that. I'll go redo that and repost it. This is the correct minimization for the sum of products. And this should be the correct minimization for the product of sums as well too. I'll go make those corrections and re-upload it. But that will take me a little bit of time to go through and make sure I don't insert another typo into this. Thanks for catching that. Sorry about that. Should we be putting this whole minimization part into the preliminary work in the lab report? Yes. So you should, whenever you do a derivation, right, you should always type up your formulas in your report. You can either put the minimized form in the main body of your report and then show the work in your appendix, or you can show the work in the main body if you want, if it's a major part of the lab. But yep, anytime you do any sort of design or derivation work and all those formulas, that's the worst part of being an engineer. in my opinion, is typing all those formulas into the report. There are equation editors you can use. Microsoft has a built-in equation editor. That's what I've used there to type it, but you can do things, Mathematica, other equation editors, and do a copy and paste into your program. But yeah, you should always type your formulas in. If you give me a handwritten picture of them, that shows your work, but there will be a deduction for having handwriting in your report. All right. You're welcome, Matthew. All right, so any questions, let's see, in terms of the lab, in terms of the Verilog, or what you're going to be doing in the lab? You guys, what is 184%? That's a little big. All right, so yeah, in today's lab, that Verilog part you mentioned, using named instantiation versus ordered instantiation. Yes, and I'm going to want you to use named instantiation all the time in this class, which I covered in the video tutorial, but I will cover again. So actually, let me do that now. Let's do an example of named instantiation. And all right, I'm going to start up Quartus, so I can show you the difference between the two. And I'm going to do it using Verilog bitwise operators. For this lab, you are going to use gate primitives, but for the next lab, you're going to use bitwise operators. So I'll show you how to solve this lab using bitwise operators and then do the named instantiation. Okay, so new Quartus project, new project wizard. All right, next. Desktop. All right, call this one practice. All right. And, all right, I don't need to set anything else. And next week, when we start working with the boards, I've posted some things regarding the lab for next week. We're actually going to have to start setting this section for our board, for our device, but I'm just going to hit finish for now because this won't go on a board. All right. Spinning wheel. All right. I'm going to get a new file. All right. So a new Verilog HDL file. All right. And I'm going to put in a comment here, and I'm going to grab that equation out of the other document. Like, give me this. I like to put comments in my modules. Right. Especially to let me know where I should be seeing my ones and zeros, because I'll find a lot of students, especially a lot of times you'll go to do your demonstrations or you'll ask a question and I'll ask you for what input what output should be generated for the input you're having trouble with. And it's hard to answer if you don't have something in front of you telling you what the output should be, especially when it comes to when you've got minimization. All right. And so let's just do the long canonical route for this one to start with. So whenever you write a Verilog module, write keyword module. I'm going to just call this Canon SOP. You name the module and then fill in your port list. And in the port list, right, we have to say what direction. Like when you pick pins in the schematic, you have input pins, output pins. So we have to give it a direction input. We give it a type wire. If you don't type in the word wire, it will assume it's a wire type by default. I forget once in a while to do that, but it's good to type that in to make it clear, because in a few weeks we'll get to where we work with another type. You want to make it clear which type you're working with because they work differently. Okay, input wire. So A, B, C, D. You don't have to space separate them. You could put these on separate lines. And what happens is once I specify this is an input wire type, every signal I type after this is going to be 1 bit. So everything in the list following that will also be 1 bit in size, and they will all be considered inputs. I don't have to individually say input wire A, input wire B, input wire C. And then if I want to start specifying a list of outputs, output wire, and I'm just going to call this one F. And at the end of your port list, semicolon, it's a common syntax error that will pop up for getting the semicolon there. Okay, we have module and module. And what we want to do then is in the canonical form, with bitwise operators, I could write this all as one equation, but I'm actually going to write out the separate min terms here. So if I want to create some other signals within the Verilog module itself that don't link to the outside world, and by the outside world meaning anything that's in the port list is something we can connect to, right? When we create an instance of this. Same way when you made block symbols, you could connect to these. But if I have other signal names, like internal wire names, like in the schematic in the tutorial, when I named those wires, well, those things are internal to the module. So I'm going to create some internal signals here, and I'm going to call this min-term 2. It could be less verbose. Min-term 3, min-term 7. And so all of these are going to be 1 bit in size. We in about 2 weeks, we'll probably start working with multi-bit signals, but for now, just 1 bit. So we won't have to worry about saying the size. So min-term 8, min-term 9, min-term 12, min-term 13. Right. And what I'm going to do then, like I said, what you're going to do this week is you're going to use gate primitives, right? And a gate primitive in Verilog, if you need a NOT gate, if you need to come up with, say, the signal A dots. So if I also had signals like signal A naught, and if I was using a gate primitive in Verilog, I'd say not. I'd have to give it an instance number. And whenever we use gate primitives, the first signal in the list is the output. So if I want to create A naught, I list that as the output, and I list then the input as A. Right? You'll be doing something similar to that today, right? And that would give me the signal A naught, right? Well, what's nice with bitwise operators that we're going to start working with next week in Verilog is you don't have to use all these primitive gate instances, because by the time you type all of these, it's not a whole lot faster than when you have to just insert all the schematics. It's probably slightly more error prone. So what we do in order to generate signals like A naught with bitwise operators is I could simply say assign A naught equals, so new keyword. This is called continuous assignment. The keyword is assign, meaning it's a reserved word of the language. You can't use it for any identifier name. And what I want to do is I want to assign to the signal A naught. So we use the equality symbol sign, the equal sign, and this is called an assignment operator. And it always assigns whatever I have the expression on the right-hand side. So I'm going to say not A. And this is the Verilog bitwise operator for not, the tilde. So if I put a tilde in front of a signal, so these two things are equivalent. This uses the Verilog gate primitive. The gate primitive is not, and I would need an instance number. So if I'm using gate primitives in Verilog, to create that A naught signal, I have to do something like this. Right? With bitwise operators, I can use the tilde for the not Just put the signal name here and assign it here. I don't have it to have an instance number. And what's nice is I can start shortening things up. I don't have to make all these individual signals. What I can start doing is I can say minterm 2 should be not A. Actually, let me put a little comment here, right? So minterm 2 we write as A naught, B naught, C, D, D naught, right? Because 0, 0, 1, 0. And so using the bitwise operators, I could say not A. The and symbol in the bitwise operator is the ampersand, not A, and with, not B, and with C, and with not D. If I put a semicolon after that, then I could start using this signal minterm 2 to come up with my out, or in my output F. What I want to do is I want to eventually have something that says assign to F the result of minterm 2. And so these minterms are going to be all of these products. I need to sum the products, and the summation, the bitwise OR, is a vertical pipe, which is usually above your enter key on your keyboard. You have to hit the shift key. It's usually right above the backslash. And so that is your bitwise, Verilog bitwise operator OR. Because what I want to say is minterm 2 ORed with minterm 3, ORed with minterm 7, ORed with minterm 8, ORed with minterm 9. And you can use more than one line. Mine's taking up a lot of room because I have the text a bit bigger. Minterm 13. So if I assign to my output signal F the results, and I have to create all these minterms, I haven't done that yet, but we want to end up doing something like this to give that canonical sum of products expression, right? This is the canonical SOP expression. And I can put in another comment, the tilde character is the Verilog bitwise not operator, right? Typically, we don't put these sorts of comments in our code. I'm doing this if for some of you that are new to this, if you want to go back and view the recording to see this as a reminder of what these are. And the ampersand character, shorten this up, character is the Verilog bitwise and operator. And so these operators work, the and operator, the not operator, the or operator, they have same levels of precedence as the gates. So remember, when you're working with Boolean expressions, parentheses have the highest level of precedence, not has the second highest level of precedence, and has the next highest level, and or has the lowest level of precedence, and precedence being order of operations. Well, that applies as well here, is that all of these nots will be performed before the anding is performed. So you don't have to put parentheses around this to indicate, well, to perform that not operation. You can put parentheses if that helps you understand it, but you don't have to. But that's going to give me minterm 2. And I promise, Matthew, I will answer your question about named instantiation. I'm just doing a review of, for people that have seen the bitwise operators, for those of you that haven't seen them, a fast introduction to them. All right, so let's go ahead and do minterm 3, which that should be A naught, B naught, C, D. So we say assign to our signal name minterm 3. So remember, signal name on the left, this is what gets overwritten. Think of this as basically, well, we'll call it an output, but the signal and the expression on the right gets evaluated. So this expression on the right gets evaluated and assigned to this. Right, and basically what this is right here is we've got a 4 input AND gate.
You want us to use the assign for this lab?
No,
Okay.
the instructions say to use the gate primitives for this lab. This is what you'll be doing in the next lab. All right, I wanted a faster way, faster until I started going into all the syntax of the language to show you named versus ordered instantiation. All right, so min-term 3, right, should be not A, and you can use copy paste here at times to help yourself, and it would not B, and it was C, and it would B. And we can assign to min-term 7, right? That's going to be not A, and with B, and with C, and with D. So spaces aren't required. Assign to min-term A equals A and with not B, and with not C, and with not D. Min-term 9, and that's A, and with not B, and with not C, 1, 0, 0, 1, and it would be min-term 12. 12 is 1, 1, so A, and it would B, and it would not C, and it would not D, so 1, 1. That's our 1, 1. Oh, 1, 1, 0, 0. And finally, 13 is 1, 1, 0, 1. Term 13 equals to A, and it would B, and it would C, 0, not C, and it would D. All right. And technically with bitwise operators, I could have taken all these expressions and just typed them in here and written one long expression. But I wanted to at least write out this example showing the min-terms, maybe make the code a little more self-documenting. Right, this then would be a module for the canonical sum of products using the bitwise operators. I need to save it with that name, so I'm going to copy this, Control-C, Control. All right. And let me set that is the top level and do a quick syntax check here. So it's top level analysis and synthesis, right? Should tell me whether the syntax. It's giving me the warning about number of processors. If I want to get rid of that warning, if I don't want to see that, I can go to assignment settings. Under compilation, I can say use all available processors. Okay, I won't see that warning anymore. All right, looks like I did not have a syntax error. All right, so if we're going to create some sort of top level module, so file new, Verilog file, module, I'll call this top level. All right, input. You can use the same signal names. For right now, I'm going to use different signal names. Look at my wire in, what wire. So I'm going to CSOP. All right, you can use the same signal names A, B, C, and D. I'm using different ones for a second to indicate when we instantiate this, which signal is which. All right. Ordered instantiation. Right, like I said, a lot of times what I like to do is I like to just copy paste the port list from over here. There's a comment, so I can see then what the order is. So if I want to create an instance of a module, right, I have to use the module's name. So the module's name is Canon SOP. I have to give it some sort of unique instance number. So I'll just call it inst0. And then I have to say how I want to connect signals in this module. So how do I want to connect signals in the top level module to signals in the other module? So if I wanted to connect W to A, X to B, Y to C, and let's connect Z to D, and C SOP to F. I guess I could have capitalized that. I'm mixing my cases. All right. So if that's what I want to do, ordered instantiation means, right, name of the module, instance number. Here, then in the port list where I specified the connections, I can just say W, X, Y, Z, C, SOP. And what that does is I use these names, right, are the names, signal names from the module I'm currently working in. This will connect this signal to the first signal in the canonical SOP port list. So the first thing in the canonical SOP port list is A. Right. This will connect X to B. This will connect Y to C and Z to D. And you know, if you have a fairly simple circuit, it's a faster way than named instantiation. This will connect then our output CSOP to the output F in that module. It's a quick way, but as your top levels start getting bigger, as your circuits start getting more and more ports or signals in the port list, it's easier to troubleshoot if you use named instantiation. And so, is it named instantiation? I'm actually going to named instantiation. It doesn't matter what order I use to connect the signals. So again, I have to use the name of the module I'm trying to create an instance of. Right. Typically, we don't create two instances of the same. Well, typically, I wouldn't do this twice. What I'm saying is I wouldn't use ordered and named instantiation if I just need one instance of this. Right. But now I can be very specific. Right. Now I can use the dot operator and the names of the signals in the port list here. So A, B, C, and D. And I can specifically say, I want to connect to signal A. So the dot operator followed by signal names and use the signal names in the port list of the module you're instantiating. So what I want to do is I want to connect W to A. Comma separated dot B. What I want to connect to signal B in that canonical sum products module is I want to connect my X. What I want to connect to Y is I want to connect, what I want to connect to C is my Y here. And what I want to connect to D is Z. And what I want to connect to F is C, S, O, P. Once you get used to this notation, this is easier to troubleshoot because the signal names in the parentheses, inside the parentheses, are signal names that are associated with the level, with the module that you're currently working in, this module. The signal names follow the dot operator. Those have to be signal names that are in the port list of this module. Right. Now, like I said, the order isn't important. If I wanted to connect out of order, I could do this, but if I then change this, ordered instantiation says, first thing in the list, X here will connect to A. Second thing in the list, W will connect to B. The thing I don't like about ordered instantiation is if I get the order wrong and my circuit's not working correctly, then, well, with experience, I know to go back and check the order. If I meant to connect W to A and X to B, and I get the order wrong in ordered instantiation, it's a little more difficult to troubleshoot. Where here, this is very specific. I can look at this and say, did I correctly connect my signals? If I really wanted to connect X to B, I can see that, yes, I've done that. I don't have to flip back and forth between modules and check order. And it's easier for me to grade. It's usually easier for you to troubleshoot when I start asking you, did you mean to connect X to B? Sometimes you'll get your, when we start working with individual bits, we're going to start working with bus signals and individual bits. Sometimes you'll be connecting the wrong bits to the wrong signals. It will be easier to find for both of us. It's more self-documenting code. And let me just change this back here. So like I said, name instantiation, you connect in any order. You don't have to match the order to the port list. I usually match the order. Most of the time I do. It's just easier when I'm making connections for me to go back and forth to check. Right. But that's how we do then named versus ordered instantiation. So a very long answer to your question, right? But does that answer your question, Matt? Good. All right. So that's a little preview of bitwise operators for next week. All right. Other questions? Let's see. Okay. Well, I will let you get to work on the lab. Like I said, I'll be here on Zoom. I'm going to go through that solution and correct it for the missing term, because I've got to add that into each one of those steps of the Boolean algebra. All right. And hopefully not make another typo. Are you going to have a tutorial for lab 3? What kind of tutorial do you need for lab 3? So yes, I will do one on the hardware. Yes, I will do one on, I think I've already got one out somewhere on Verilog bitwise operators. Yeah, so I will post a YouTube video. I may have to record a new one. I've got some on Verilog bitwise operators, and I will likely post that tomorrow. You're welcome, Solomon. All right, cool. All right, like I said, all right, I'll let you get to work on the lab. I'll make those corrections and I'll be here to answer any questions.
Professor, so for the lab in Verilog, do I have to create variable for each min term, or can I just group them in one SOP?
For this particular lab, you're going to use the Verilog gate primitives, so you're going to have to create a named wire for each min term, each max term. For bitwise operators, you can write everything out all in one, but for the lab you're working on this week, you cannot use bitwise operators.
Okay, thank you.
You're welcome.